Today, we want to continue finding some Taylor polynomials and some Taylor series, and let's look at a new function. The main way we're generating Taylor series is by looking at Taylor's formula, taking a given function and approximating it near a given point. Let's start with one of the weird way I phrase this one. Instead of saying find a Taylor polynomial of a specified degree, I just said find the first four non-zero terms of the Taylor series approximating cosine of x near x equals 0. And the reason that I said this will become evident why I said first four non-zero terms and not fourth degree Taylor polynomial. And it's because half the terms are going to be 0. And I want to make sure that we get enough to build a pattern so that we can stop finding all the terms. Let's begin. What we need is the function and a bunch of derivatives evaluated at 0. So let's start with our function f of x. The first derivative, f prime of x, is negative sine x. And at this point, we want to remember that we're evaluating at 0. So we're going to want to f prime at 0. Sorry, f at 0, which is cosine of 0, which is 1. But as soon as we get to f prime of 0, negative sine of 0, we get 0. So right now we've got one term. And this makes sense. The equation of the tangent line for cosine of x at 0 is just the horizontal line y equals 1. So let's find some more derivatives. F double prime, derivative of negative sine is negative cosine. So f double prime at 0 is negative cosine of 0, which is negative 1. F triple prime is back to sine, or not back to, but is sine. And so the third derivative at 0 is also 0. Even though we've taken 3 derivatives, we've only got, even though we have 4 derivatives, we can just start with the 0th derivative. Even though we have 4 derivatives, we've only got 2 non-zero terms. So we keep going. What we notice is that when we get to the 4th derivative, and we probably saw this coming because we know what happens when we have a bunch of derivatives with cosine. The derivative of sine is back to cosine x. And we're back to our original function. So now we're in a loop. So cosine of x, we're back to the start, is also cosine of x is the original function. It's also the 4th derivative. And so we're back to the start here. The 4th derivative evaluated at 0 will be back to 1. If we take another derivative, the 5th derivative will be negative sine x. And so the 5th derivative evaluated at 0 will be 0, and so on, because we're in a loop. So when we start building the terms in the Taylor series, we're just going to follow the pattern: 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. Remember our formula for a Taylor series is a sum as n goes from 0 to infinity of the nth derivative evaluated at a divided by n factorial times x minus a to the n. In this case, a is 0. Our function is cosine. When we're finding all these derivatives, we're just figuring out the numerator of the coefficient in the general term of our Taylor series. So we start with f of 0, and then f prime of 0, a, times x minus a. The derivative part that we find is just the numerator of our coefficient. 2 factorial is there because we built this polynomial by matching derivatives. That 2 factorial is there to cancel out the x squared, the 2 from the x squared. The 3 factorial is there to cancel out the exponents as we take derivatives. So we're just here to fill in the numerators from those derivatives. So for cosine x, our Taylor series we'll start off with f at 0, which is 1, plus f prime at 0, which is 0, times x minus a, which is just x. The next numerator is f double prime, which is -1. All this part, the x to the n over n factorial, that's all from Taylor's formula. We're just filling in the numerators. And we saw, because we started with cosine, that we're just going to cycle through 1, 0, -1, 0, 1, 0, -1, 0, and so on. The numerators we get from the derivative, the denominators are the factorials, and then we get the x factors in each term. So this is why we wanted to specify the number of terms that we want rather than the degree, because we are only getting even degrees. This makes sense. Cosine of x is an even function. Cosine of -x is equal to cosine of x. So we're not surprised because the function does that. It's even. Because the function is even, we're not surprised that we only have even exponents in its polynomial representation. So here are the first 4 non-zero terms of the Taylor polynomial, of the Taylor series, approximating cosine x near x equals 0. This is one that we should remember. This is one that we should recognize. We can summarize this. We could say this is the sum as n goes from 0 to infinity. And let's look at the 3 elements. We've got the alternating. We've got the x to the even number divided by the factorial of that even number. So let's put a -1 to the n to get that alternating. We're dividing by, it starts 0 factorial, 2, 4, 6. So we'll have a 2n factorial. And then the exponent on the x is also 2n to make it even. We can do a similar thing and write down the Taylor series for sine x, because we've done all this work so far. We shouldn't just ignore that. We recognize that that happened. And know that if I want the Taylor series for sine of x, I can just start with the third derivative. We have sine of x, and that's going to start off with a 0. So to make our, if we start off with g of x equals sine x, so let's now do g of x equals sine x near x equals 0, but let's not do so much work. Because that's the goal. We're in a math class. We're trying to figure out how to do less work. I know it doesn't come off that great when we do it this way, when we say it that way. But the whole point of all this math, the whole point is to do less work. The point is to do less work. We do all this work in math so we can do less work. We do the math so we can figure out how much weight the bridge can hold without having to do Calvin's father's plan and say, well, we just drive trucks that keep getting heavy over it. And then when the bridge collapses, we just weigh the last truck and rebuild the bridge. We don't want to have to rebuild the bridge all the time. Build a bunch of bridges and destroy a bunch of trucks when we could just do a math problem. This is why, although I love the show Mythbusters, really gave you the wrong idea about how stuff works. Most Mythbusters episodes are a math problem. And we did all this math. We spent the last couple thousand years developing math so that we wouldn't have to do Mythbusters. And yet, what do we all watch? Mythbusters. When Mythbusters came out after a couple of episodes, math was just standing in the corner of the room with his hand on his head saying, well, fine. Anyway, we're just starting off with this sine x, right? If our function g of x is sine x, we know we're going to go through the same 4 functions. We just have to figure out where we're starting. Our g of 0 is 0. Our g prime of 0, derivative of sine is cosine. So we're starting here with the 0. And then g prime is cosine, which is going to give us a 1. So g prime of 0 will be a 1. And now we know where everything else is going to be. G double prime of 0, move back to 0. G triple prime of 0 will be at -1. The fourth derivative, I wrote this sideways. It's supposed to go up and down. Oh, well. our fourth derivative. Here's our fifth derivative. Here's our sixth derivative, and so on. Because we know we're going to get the same four functions, so we're going to get the same four numbers at 0, 1, 0, negative 1, 0, 1. So we get this structure from Taylor's formula, x to the n over n factorial. The numerators come from the derivatives, and that's just going to follow the pattern. 0, 1, 0, negative 1, 0, 1, 0, negative 1. And so we get our first four non-zero terms for sine of x with x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. We're not surprised by this. Sine is an odd function. Sine of negative x equals negative sine of x. So we are not surprised that we get only odd exponents. Because if we plug in negative x, we're supposed to come up with negative x. We can summarize what we see here by noticing the pieces that we want. I want x to the odd over odd factorial. I want those parts to match. And they always want to be odd. And we also have this alternating thing that we need to do. So I've got to alternate starting positive. So I'm going to have a negative 1 to the n. Now I've got to make an odd number for all the integers. I've got to take all my integers and make them odd. To make them even, I did 2n. To make them odd, I'll do 2n plus 1. I'll say 2n plus 1 because I'm starting off with 0. Two n makes the n even, plus 1 makes it odd. Make sure it starts off right. When n is 0, I get 2 zeros plus 1. That's going to give me 1, and that's where I want to start. So I'll have x to the 2n plus 1 over 2n plus 1 factorial. And I'll make it alternate. And now we have the Taylor series for sine x. Then we might notice some cool stuff. Remember that sine and cosine are related. The derivative of sine is equal to cosine. So if I look at this second Taylor series and I take the derivative, The derivative of x is 1. The derivative of minus x cubed over 3 factorial will have 3x squared over 3 factorial, and the 3's cancel out, leaving 2 factorial. So the derivative of minus x cubed over 3 factorial is minus x squared over 2 factorial, and so on. The derivative of 5x, x to the 5th is 5x to the 4th. The 5's cancel out, leave the 4 factorial in the denominator. That's the next term of cosine. So we can take the derivative of our series representation of sine and generate the series representation of cosine. And just like that, in the last 2 minutes, I have said quite a lot. First of all, I wrote sine x equals this series. And normally we're really careful about that because in algebra, a lot of times we just write a bunch of steps in an equation and we'll just put equal sign in between all our steps. And so we don't notice that we've said something ridiculous that like 5 is equal to 0 because we just keep putting equal sign in between our steps. So I've made a bold claim by saying sine of x is equal to this power series. It's because I put an infinite number of terms. That's why they get to be. We also should think about where this is appropriate. We know that the Taylor series is a power series, and a power series has an interval of convergence. So we should think about the interval of convergence. This x to the 2n part, that doesn't tell us much. That just says that we'll get convergence between -1 and 1. But the coefficient has a factorial in the denominator that's unchecked by a factorial in the numerator. And that indicates that our interval of convergence is all real numbers. We ran this through the ratio test. And then this 2n plus 1 factorial would leave 2 factors of n in the denominator, unchecked by any factors of n in the numerator. So when n goes to infinity, the limit from the ratio test will go to 0, which is less than 1 for all values of n. So these two power series for cosine and sine converge for all x. This is different than the series that we saw yesterday. The series we saw yesterday for natural log of x only converged from 0 to 2. It was conditionally convergent at 2, but divergent at 0. So that power series representation only worked between 0 and 2. This power series representation works for all x. Now, if we are far from 0, we may need to use a lot of terms. But if we're near 0, we get convergence pretty quickly. Let's take a look at this. Let's watch this converge. Uh-oh. I don't have a Desmos open. Let me open up a graphing calculator. So here's our tangent line for cosine of x. Make it stand out more. There's our tangent line, and let's just start adding some more terms. The next term is x squared over 2 factorial. Now we can see that this polynomial looks like a polynomial graph. It's not going to look like this periodic sinusoid, but near 0, it looks pretty accurate. Near 0, cosine looks like a parabola. So if we zoom in, we see that they're very close. If we don't like how far apart we are, then we just zoom in some more. And we say, look, see, they're no different at all. We can just keep doing this forever. And if you zoom in close enough, things aren't very different. When you kind of pull back. So, all right, let's improve our approximation with some more terms. So we throw another term on there. Now we've got a fourth degree approximation. Now, the fourth degree approximation is closer, near zero. It's closer, and it works over a wider interval. And so we can zoom out a little bit more and see how things and see things very close. If we throw on more terms, now where we saw differences at the end, now that we have more terms, we don't see any difference until we zoom out a little bit. Because as x goes to infinity and negative infinity, polynomial is going to polynomial. Meanwhile, our sinusoid is going to sinusoid. The more terms we use, the better the approximation gets. It gets closer to our original function, and this works over a wider interval. Any questions? Comment? Do you comment? Because of the nature of these functions, we don't really need all that much, but that's specifically because we have a periodic function. So, oh, can I do this? It's a periodic function, so if we want to look somewhere else at some different interval, we can just shift everything. Our function will go, our series will go back and forth, just like the function. Wait, this is going to cause anxiety if I just left this running. So not only did I use equals, I said sine equals this power series. I also said, hey, if you take the derivative of sine, you get cosine, and that works in the Taylor series as well. That says a lot. We can just manipulate the power series the same way we manipulate the functions with derivatives. We treat these as separate terms. Treat it like a polynomial. So one of the important things that we get out of these Taylor series, remember, one of the important things that we learn in a math class is that we should be avoiding doing any more math. That's the whole point. The reason that you learn this stuff is so that you wouldn't have to use so much math. Let's suppose that for some reason we need the Taylor series for sine of x squared. We want to use the fact that we already know the Taylor series for sine, and we just want to plug in an x squared. Spoiler alert, we're just going to plug in an x squared. Let's talk about y, though. If we start off with this function, h of x, if we're just going to find the Taylor series starting with this, it's going to get really messy really fast. Because when we start taking derivatives, we start having to use the chain rule, and then it's just going to get worse from there. So h prime, finding h prime is no problem. Derivative of sine of x squared is cosine of x squared times the derivative of x squared, which is 2x. No problem, except that we still haven't got a non-zero term for our Taylor series. But now we've got to find a second derivative. And so now we have to use the product rule. So for our second derivative, we'll need to take the derivative of the first times the second, plus the first times the derivative of the second. Now, let's just write it out. It's going to be messy anyway. Plus the first times the derivative of the second. Derivative of cosine of x squared is negative sine of x squared times 2x. So we get 2 cosine of x squared plus minus. That's why I erased in the first place. Dude, you just erased 4x squared times the sine of x squared. We're only at the second derivative. We already had to use the product rule, and I like to avoid using the product rule whenever I can. That's just work. And now I've got 2 terms. I need the chain rule on the first one. I need to use the product rule on the second one. And we're all set. It's like, oh, dude, I passed this class. Why do I have to do it again? So, taking derivatives is a little bit messy. Now, we could throw a computer at the problem, but if we're going to throw a computer at the problem, let's just ask the computer what the series expansion is for this function. Because, I mean, if we're going to use computers, I'm not going to use computers for a part of the problem. Use computers for the whole problem. We don't even have to be specific. We could just be like, oh, hey, Wolfram Alpha, sine of x squared. And it'll start just telling us stuff. Like the series expansion. Might be too bright. Wolfram Alpha needs a dark mode, I guess. Oh, here's some more representations. Here's some, integral representations. I don't want things to be too interesting. So we don't want to take these derivatives. So we're just going to take our series for sine of x. And I'm going to plug in x squared. I'm just going to do the composition here. rather than take all the derivatives, just take our series for sine of x and plug in an x squared. This says a lot. This says, first of all, that you could use these just like we would use any other function. Use this power series just like you would use any other function. Want to evaluate it? Evaluate the series. It's just an infinite number of terms. But it's cool. We can see the whole pattern. We're not surprised that we ended up with an even function because I plugged x squared into the sine function. I started with an odd function, and then I made the argument of that odd function x squared. I made it even. So now if I plug in negative x, the first thing that happens is that that negative x gets squared and it becomes positive x. If we're wondering, gosh, how are we going to describe these functions? We've already done it over here. I just need 2 times 2n plus 1. So my series, my representation will look like the sum from 0 to infinity. I still got the alternating parts. The denominator is just still these odd factorials. But now x is being raised to the 4n plus 2. That makes sense. It's starting off at 2 and increasing by 4. We got 2, then 6, then 10, then 14. So the fact that we can just use the series representation and plug stuff into that, that's very powerful. If you recall, this function sine of x squared does not have a nice antiderivative. And by nice, I mean it does not have an antiderivative that can be expressed finite combination of elementary functions. Sine of x squared is not the derivative of some finite combination of elementary functions. So if I want to express the antiderivative of sine of x squared, I have to use either a finite combination of non-elementary functions or an infinite combination of elementary functions. I have to break one of those two requirements. So to make a nice antiderivative, I either have to use non-elementary functions and say use the second fundamental theorem of calculus to say capital F as the integral from 0 to x of sine of t squared dt is an antiderivative of sine of x squared. Or I can write an antiderivative that's an infinite combination of elementary functions. So to write an antiderivative of sine of x squared, I can either use a finite combination of non-elementary functions or an infinite combination of elementary functions. Elementary functions are the ones that you've encountered so far. The only non-elementary functions you've come across are antiderivatives that must be constructed by the second fundamental theorem of calculus. This creates a cheat code for any quiz where I say, find the antiderivative of the function or write the antiderivative of the function. You don't actually have to do any work. You could just use the second fundamental theorem of calculus and construct them all. Even if I said something simple, like I said, find the antiderivative of x squared, you could say it's the integral from 0 to x of t squared dt. I don't know if I would try that with any professor other than me. In the history of my teaching, I've had one student notice this loophole. They got stuck on a problem, they were pressed for time, and so they just used the second fundamental theorem of calculus. I was like, oh, all right, that's fine. I didn't specify that you had to use integration by parts. Then I had to test it out. I said this I intended the problem to be done. And then I had to put it on another quiz. I put a slight variation of that problem on another quiz, and that student switched tactics and they just did the planned thing. On one hand, I was like happy that they learned the process. On the other hand, I was a little bit sad that they didn't stick to their guns and say this worked last time. I got 4 out of 4 for using the second fundamental theorem of calculus, rather than take a 0, but they just did the normal thing. They did what was expected. Anyway, that's going to do it for today. We'll talk a little bit more about Taylor series and Taylor polynomials tomorrow. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.